So let us start with a few quick questions which will give us a chance to review the concepts that we have studied so far. So I want to reinforce the concept of linear phase. Okay, I want you to think about an answer, true or false or yes or no type of question. So question number 1. Can a LTI system, so remember if I have h of n can be finite length or it can be infinite length, right? Impulse response corresponding to the LTI system. These systems I'm going to call as finite impulse response systems. Impulse response systems, FIR. Okay, very important acronym that we often use in discrete time signal processing. FIR means an LTI system represented by a impulse response that is finite in duration. And correspondingly, we have an infinite length system. We call it as infinite impulse response. Infinite impulse response. FIR and IIR. These are the two categories that we will encounter in terms of LTI systems, IIR. Okay, so using that acronym, can an IIR system, LTI system, have linear phase? Can an LTI system IIR have linear phase? Yes or no? Okay, and whenever there's a question like this, all you need to do is find one example which will give you a reason to say, can it be? So we're not saying that all IR systems are linear phase, not like that. Can you find one IR system that has got linear phase? Yes. Which one is it? Ideal low pass filter. Ideal low pass filter. It is infinite, it's a sinc function, it is doubly infinite actually, it goes both to positive side and negative side, and it can satisfy linear phase. So second question, can FIR systems, LTI system, have linear phase? Have linear phase? Of course, this is sort of trivially answered. Yes, because when you truncate an IR system, just like we did a truncation of a, so this will also be yes, we can always satisfy. So in both of these cases, the property that we are relying on is not the length, but the linear phase depends on the symmetry. Depends on the symmetry that is present within h of n. Symmetry in h of n. Okay, not on the length. So that's an important aspect that we want to carry forward. Now, notions of causality. Okay, linear phase we have covered. Now let's look at the aspects of causality. Okay, number 3. Can an IIR filter be causal? IIR filter be causal. Okay, this is a new notation that we have introduced, IIR. So you may get confused. You're thinking of the sinc function doubly infinite. You don't have to always think of it like that. So consider a impulse response that is of the form a power n u of n. Is this IIR? Yes, infinitely long. Is it causal? Starts at time n equal to 0, goes to n equal to infinity. So yes, this is possible. Okay. Number 4. So important that we are always looking at those properties in a very practical way, looking at with the context of examples. Okay. So can a causal IIR filter have linear phase? have linear phase. Basically, we are combining causality and linear phase. Okay. This is a very important question to handle, because we are looking at saying, okay, I have an IIR filters can be linear phase, no problem, right? FIR filters can be linear phase. IIR filters can be causal. Now we are asking a question, can an IIR filter, causal IIR filter, basically it starts at time n equal to 0 and goes to infinity, can that have linear phase? The answer is no. Why? Because it is going to infinity on one side. Remember, we should have symmetry. So at some point you should have symmetry, but on the left side you always find that there is only a finite amount of samples are available, whereas on the right hand side it will always be infinite. So symmetry will not be satisfied when you have a causal IIR filter, and therefore this system cannot have linear phase. This will not have linear phase. So again, important to keep all of these concepts so that we are able to apply them in a good and with full understanding. You are able to apply them. Now let me also quickly add on to it the aspects of BIBO stability. Okay, so BIBO stability, another important aspect that we have already studied in chapter 2, again comes back to in terms of the concepts that we are discussing currently. BIBO stability. BIBO stability basically says that you want to have the DT/FT to be bounded at all frequencies. That is what BIBO stability is. So all frequencies, you will find that there is a finite gain that is given by the LTI system. And this translates into a condition that the DT/FT mod h of n, this leads to absolute summability. So this is the absolute summability condition, which is also linked to BIBO stability. Summability. Okay. Now we have related, when we studied the Z transform, we related the absolute summability condition to the existence of the DT/FT, and we also related it to the condition on the Z transform, including the unit circle in its ROC. So basically, if I ask you how do I satisfy BIBO stability, you look at the Z transform. If the Z transform has an ROC which includes the unit circle, you can confidently say that this LTI system will be BIBO stable, its impulse response will be absolutely summable. All of those things can be readily stated from there. So this condition, absolute summability, is now related to the Z transform having an ROC that includes the unit circle. ROC that includes the unit circle. That includes unit circle. Okay, so I hope you are comfortable with that statement. And now we then say that the ROC included in the unit circle means that if I am talking about a causal stable system, causal and stable system, this means all poles inside the unit circle, all poles inside the unit circle. Okay, and that is also the necessary, that's a condition that we need to have the BIBO stability. Okay, so now comes the final statement. So supposing I want to understand the aspects of causality and stability for an FIR system, LTI system with a finite impulse response. Okay, and of course in all cases we are looking at a causal system. Where are all the poles? Poles are at z equal to 0. All the poles are at z equal to 0. Okay, there are no poles anywhere in the rest of the Z plane because it's a causal system. So an FIR system will always be BIBO stable, which again which we knew from the past, and we also now can use this information to our overall understanding of LTI systems, that this is a important condition. Now, on the other hand, if you have an IIR system, BIBO stability, again for a causal system, this requires all poles to be inside the unit circle. Poles inside the unit circle. Okay. Under that condition, we will satisfy the BIBO stability, and basically, so the our entire understanding of causality, stability, linear phase, everything, all of these concepts sort of come together and give us a complete picture of what we are focusing on.